This is the design day video for Team 22037 Rapid Multispectral Imaging System.
The problem we are facing is to view physiological processes with the naked human eye. With that being said, it's advantageous to be able to understand and view these, and normally that cannot be done just by looking at them. Some examples of this include blood flow as well as perspiration levels, and our system will be able to produce real-time images that current commercially available systems cannot produce. So the objectives of our system will offer an easy way to view blood content at a faster rate than commercially available methods. Our design concept involves the implementation of Python coding, which combines camera image acquisition data as well as real-time simulation of image analysis from these captured images. The objective of the RMIS is to analyze physiological processes in the human body based on the wavelength response captured by the camera. The system will then generate synthetic images to create a video of the physiological processes happening in real time. So the project focuses on software development, photo calibration, mathematical modeling, system integration.
Our approach to this problem has been to design the software for image calibration along with a user-friendly GUI. We have 4 groupings of system requirements. First, performance requirements detail the system capabilities. Interface requirements outline how the system hardware should function. Design requirements define the components and the budget of our system. And storage requirements describe how the data should be stored in the system.
About the design concept of design for a rapid multispectral imaging system. As you can see in our block diagram, the camera is set up on top with our 15 LED rings. This is outside the scope of our project. This feeds into the dotted lines, which will show all the functions that we've created throughout our time in our design project. First, you can see in real-time calibration, which feeds into storage and other calibration. All these go into the spatial and spectral calibration. We done with our images, which then goes into our real-time data analysis, which will actually create the physiological data. All these images are then shown into our user interface, which is controlled by the user, and the user can choose which functions to apply and not to apply to our system. Next, you can see the images of the laptop itself, which is connected by USB 2.0 into the camera. The camera is shown here, the image to our left, with the image on our right, but it's on the left side with the PVC wrapping around it, as well as a background in order to avoid any light exposure from the outside. The next slide shows our verification matrix. The verification matrix is showing the image acquisition rate, which is the amount of images that are coming into the system. In order to successfully run our camera system, we need at least 500 frames of data coming in order to create those frames and actually process the data. As you can see, that our system is capped at 500, but did meet the requirements needed. In our second verification matrix, you can see that the rate at which synthetic images produced is what we're looking at. And throughout our tests, we found that our system actually ran higher than the needed 10 frames per second at a rate of 11.1. And of course, the more images being processed, the better.
Here are the deliverables that we will be providing to our sponsor by the conclusion of the project. The function and code is collaboratively worked on through the team's GitHub, which involves public repositories of our code that have been shared with our sponsor. This code on the team's GitHub includes everything that we have agreed upon with our sponsor, such as the calibration and optics data, as well as the user interface and synthetic image production. The GitHub also includes installation instructions for every Python extension used, so that the project may be expanded upon in the future. Lastly, the technical data package will be a cohesive data file of the team's effort and contributions throughout the past year. So here's where our project is at right now. This is the user interface that starts, stops, and saves the images acquired by the camera. We also have functioning buttons that allow us to specifically select which images we want to save or display and how we would like them to be calibrated and analyzed. As you can see, the system operates at our anticipated 500 frames per second input. We have also largely surpassed our goal of displaying 10 frames per second as our output, since we have a consistent FPS output of around 45. We have a demonstration coming up of the system as it currently functions. Our future goals for finalizing the project include expanding the function of the buttons, being able to specifically target different types of physiological data, and then displaying that physiological data over the images. Overall, our code has been successfully integrated into the GUI.
So this is a video demonstrating the physical hardware of our system done by my teammate Hill.
Hello everyone. So this is our multispectral imaging system. So here the whole support is made up of PVC pipes, and here we have the camera. The camera is surrounded by 26 LEDs, and the camera is held by the support, which is the housing, and also we have the cooling system, and then we have the blue cable which powers the camera, and then you have the back cover cable which powers the Arduino, which basically controls the whole system when it is connected to the computer.
Here, this is a video of me demonstrating our system's GUI. So this is our graphical user interface. Here on the main screen, we have our start, stop, and save button. So start turns on the camera. I'll demonstrate it right now. As you can see, we can see whether the camera is seen. We have a status telling us start. Clicking stop will turn off the camera. And as you can see right here, on the right hand corner, we have FPS in, and then right over here, FPS out. Our default button will take us back to the original view. Here's our analysis button. Our drop-down menu that will allow us to choose from our 13 different wavelengths. And our physiological data button will create a blood-related image based on our data. And these buttons right here are for checking if we want to have the background subtraction on, or the flat field, and the data binning. Here are some problems our team have overcome. So one of them would be working with PyQt Designer, since it was a program that no one really had any experience with. The next one was connecting the Blackfly camera to display on the GUI instead of like opening up on a new window. And another problem that we overcame was getting all the different pieces of code, like the blood quantization and the data binning, to connect to each other.
Safety or other issues. The physical imaging system is delicate because it contains the hardware and the camera. So our team needed to make sure we handle the imaging system with care. Also, we had to make sure that we unplugged cords when not in use to ensure the electrical safety. Lastly, we had to be prepared for unexpected room for error, such as minor bugs in the Python code. Acknowledgements. I would like to thank Devesh and Mackenzie for all of the help they have provided during this semester. Along with that, I would also like to thank the previous design team, our team sponsor, and our team mentor for their support. Thank you.
And finally, here is our Design Day poster. It is separated into our objectives and goals, methods, results, conclusions, references, acknowledgements, and further information. We will thoroughly go through this on Design Day. Thank you so much for watching our video.